All right, so we're talking about using Calculate 84 on our smartphone. So if you will download this if you haven't already. I like Calculate 84. It gives my screen the look of exactly what a TI-84 would look like. So it transfers well if you have to come to a class with a handheld graphing calculator. You shouldn't be comfortable transferring from this to that because they're exactly the same functionality. Only the smartphone kind of has the touchscreen option where you wouldn't be able to do that on your handheld. So go ahead and download that if you haven't already. You might also use Class Calc is another option for Android. And then feel free to use any version that you find that you may find one that you think is more user-friendly, what you've been used to using, and that's fine too. But I'm going to demonstrate with Calc 84 and show you the functionality, the main white buttons you see along the top. The first row buttons, we've got Y equals, which is where you type in equations. Equations do have to be solved in terms of Y. And then the window lets you adjust. The default is a -10 to +10 X scale counting by ones. And then Y is the lowest at 10, highest at 10, counting by ones. And you can see on my graph, it counts, there's 0, back 10, over 10, up 10, down 10. So that's the standard window. You can change that though if it doesn't fit in that well. Zoom also is a way you can zoom in and out. The standard zoom takes you back to your 10 by 10 if you ever get out of that. Trace allows you to move your left and right button. Oh, where's my trace at? There it is. Moves along, it tells you the points along the curve or along your graph. So you can kind of try to estimate points that way. And then graph, of course, is the main feature that pulls up the picture of display. Second row functions, very important. They're above these. They're a second, so you have to hit second, like Y shows stat plot. Second windows table setup, so you can tell it to start at various numbers and if you want to count by ones or not. For example, you need a decimals in this, so I'm going to count half. You could tell it to count by 0.1s and so on to get the get smaller amounts in your table. But that's for X. Now Y may come out to be whatever it is, but if you want an X value that's a fraction, you have to tell it here. And that will change my table of values. Notice now in my table, which is a second of graph, you see I've got -8, -8.5. It's counting by half, so I get more values that way, more fraction values for my X. So you can do that. Also, under Calculate are important features. If you want to find your X-intercept, that's under Calculate, so that's second of trace. And you can see when you go up and down there, we've got 0. Those are X-intercepts. Let me just demonstrate that. So you can go to the left side of where I think the X-intercept is, hit enter, and then with your trace or with your smart screen, enter, and it should tell you where the intercepts are. Notice it threw me for a loop there. It says the same thing. I was thinking, oh, there's only one X-intercept, but it says the same thing. Can you see that? It says -3.000 and -3.000. So that's this point where I think the X-intercept is, and it is at -3. This other above it just tells a point where my cursor is along the curve. So that's the current cursor point. But the intercept or the 0 is given, and because it's a quadratic, we look for two answers, and this tells us it's a repeated solution. -3 is repeated. We also call that a multiplicity. At this point, you've probably been through that lesson where we call a repeated 0 multiplicity, and also talked about how it bounces on the graph. In chapter 3, we talk about an even multiplicity bounces, and so we can see that on that one. But that's how we use intercept. Minimum maximum is also under Calculate. It has a maximum that's at its vertex, so we could go to the left of where I think that is, cursor to the right, hit enter, and it tells me it's also at the point -3, -0, or -3, 0. It's also a critical point vertex. Intercept chapter 5, and then table of values, we looked at that. So those are the main functions. And you may have heard me say that before, but I like to review it. You just picked up this video. So we've talked about linear equations in earlier videos. We've talked about the quadratic equation, which you see on my screen now. We've talked about other activities like absolute value equation, the V, and then the square root equations, and more of the parabola. So today's lesson we've moved up to is 3.5 rational functions, how that we can use this to graph the rational functions. So I'd like you to plug this into your y equals, and we're going to talk about that. Now, I'm going to use a parenthesis for my denominator. There's probably other ways to get that in there, using your fractions or something you can pull up there. I've just used a parenthesis, and that's how I could type that in. And then hit graph. And notice that our rational functions are just wild looking. They twist and turn and split, all kinds of variety there. So let's talk about that. Sometimes my TI 83 or 84 had trouble whenever there was a break in the graph, and my smartphone app seems to be handling that a little better, actually, I'll have to say. But because it would connect my dots between the two curves, and here it has not. So what has happened right here? The graph has split. My first question is, what is the parent equation? So do recognize that this is a transformation of the old parent equation that we learned in a previous section for y equals 1 over x. The 1 over x graph looks like this. It has a curve in the first quadrant and an opposing curve in the third quadrant. And it has an asymptote at 0, x equals 0, and at y equals 0. Now notice that this transformation, things have moved. The 7 has affected the shape a little bit. It's kind of hard to tell so much in these, but it is a little affected. You know, the original parent function has just a 1 there, and this one has a 7. So it has a factor of 7 for its shaping, or its stretching, shrinking factor, we would call that. But you can't tell so much that on the graph. The minus has a profound effect. This moves your vertical asymptote over to x equals 2. There's a problem, and it equals to a split in the graph. I might go over and kind of get close to that to see something's going on there. I can't seem to get an x equals 2. Oh, I got it close to 2. Can you see these points? I don't know if you can see that or not. But it gets very close to 2, and I can't seem to get the graph to say 2. Also, if I look at table of values, let's see if I can find x equals 2. You know, on this side, there's my x values. I'm counting by halves, so I ask it to do that. Up at 2. Do you see that error reading? So at positive 2, there's going to be an error whenever you've got one of these asymptote lines. So this might also help you find where that's happening. So also just know that the asymptote line, the vertical asymptote line, is whatever makes the denominator equal 0. That's where the graph is undefined. So that's one thing. We're looking for these asymptote lines. So for f of x or y equals 7 over x minus 2, the asymptote is moved over 2 places, and the graph still looks basically the same, like that. So the graph is not touching at 0 either. Can you see that along this, when I get my cursor moved over, I can't get y to equal, I can't get y to equal 0 either. And you can look along this and say, does y ever equal 0? Oh, let's see, I'm getting close. Y is small there, it's getting smaller. Does it ever actually achieve 0? So you can kind of try to figure that out. And you can tell it's getting really close, infinitely close, and that's how an asymptote line will be. The values for y are getting smaller and smaller, approaching 0, we might say. But it's just not slow go, so you keep trying and see if it ever gets there. And it won't. But you can kind of play with that a little bit more at home and see what I'm talking about here. If you keep going, does it just keep getting closer and closer and smaller y values, but it never achieves 0. So that's also an asymptote line at y equals 0. The x-axis is an asymptote, as well as x equals 2 is the vertical asymptote. Okay, let's do that again. This example for you, a little more elaborate rational function. So take a minute and pause the video and put that in. use parentheses within parentheses on the bottom because I want all of this in a parenthesis. So I need my x minus 1 in a parenthesis. I'm going to need a double parenthesis here. And the smartphone does try to help you with your parentheses to make sure you close any open parentheses. It kind of seems to know more about that. Oh, I forgot my x. I think I got it. Okay, so notice I have an overarching parenthesis around the denominator, plus I have some inside parentheses there, but I clearly have the denominator with an extra parenthesis around all of that. You'll need that before you can hit graph. All right, so interesting looking graph. It's got a couple of breaks, and we can tell from this denominator that there should be two breaks. There's two values that would make x equals 0. At x equals 1, we get a 0 for this factor, and 0 times anything makes a 0 denominator. So when x is 1, we have a problem. Do you kind of see at x is 1 here? You get no value, and you can use your cursor, find out that x never exactly achieves 1. It's undefined there. And negative 2. So there's two vertical asymptotes. The vertical asymptotes are at x equals 1 and x equals negative 2. Then there is also a horizontal break. It looks almost like it's at 0, so you might jump to the conclusion that it's 0, but look in your table of values or blow your graph up a little bit more, and it actually is at 1. So I would caution you, about that, to be careful to investigate it deep. So look through here and see if y equals 0 or 1. So it looks like, just from investigating, and that's a common answer, we get y equals 0. See if, it's a lot of investigating here with my scaling. And you can't be 100% sure using the table of values because I'm only counting by halves. But y can equal 0, but not 1. 1 is the value here and here. And I have to go or investigate this deeper or blow it up. Let's do that. Let's go back to let's zoom in some. Let's zoom in and keep zooming in. See. Zoom enough in. Okay, there. I'm zooming in a little bit more. Can you kind of see that it's not the 0 that's the point, but it's this 1? And I might need to move that over some and see. But, okay, the other way I know it, let's rely back on our method for finding all the horizontal asymptotes. Let's review that. The horizontal asymptotes, there's three things that we look at to compare the numerator and the denominator degree. Compare the degree. If the numerator is a less degree, like the last one was, you get y equals 0, which is the x-axis. That's a common one. So on the last problem, we had 7 over x minus 2. So the degree of the top, we had an x to the 0. There was no x. So the degree was smaller than the bottom. And that's why the asymptote was at 0. Another example would be x over x squared. As long as the top has a smaller degree, or 1 over x squared. All of those have an asymptote at 0. But our example here, they actually have the same degree. The numerator and denominator have the same degree. Let's look at it. We've got x squared over, now it looks like I've got, x to the first, but when you multiply, this denominator is going to be x squared plus x minus 2. It's just in factored form. So it's x squared over x squared plus x minus 2. Same degree. When it's the same degree, x squared over x squared, we divide the numbers in the lead. And that's where we get y equals 1. So that's where your horizontal break in your graph is. So again, use your calculator to kind of help you, but also know your rules and investigate it that way. While we're at it, let's talk about the third rule. What if the numerator has a larger degree? I'm not going to have time on this video to do, but let's say we had x squared plus x plus 1 over x minus 3. We have a larger degree than the bottom. If it's larger by 1 degree than the denominator, we do synthetic division. So x minus 3 would use positive 3, and the coefficients of our polynomial, and we multiply and add our way across, throwing away the remainder, and this is the equation of the asymptote, the third possibility. It's called an oblique or slanted asymptote. And you get this slanted line that the graph will go around or be split from when the degree is an x squared over x, basically. When you have a higher degree by 1 than the denominator, you do synthetic division and you have a slanted asymptote. All right, hope that helps. We can do more of these. If you contact me, let me know if I can help you. Best wishes.